In this series of videos, we're going to investigate low-power radio networks and how you can use them to connect your own thing to the Internet. In part 1, we will begin by explaining the basic elements of the Internet of Things and some terminology involved. We will then take a particular example from setup to the point where a live connection can be proven and connected using any web browser. In part 2, we will then go behind the scenes and investigate the various ways in which systems may be programmed to send and receive data and interact with all the differing mechanisms used to process, store and react to the real world. In part 3, we will build on the experience of the first 2 parts and consider other hardware platforms and software options and how these too may be configured. First, a little housekeeping. This video was made at the beginning of 2017 and is probably going to be out of date even before it's been uploaded. So, apologies for the slightly stale smell. It's also been produced with a heavy UK bias, as many of the settings have been tailored to the UK's digital Catapult programme. For toilets, follow your local route, and if you do hear a fire alarm, panic, as we have edited out all of ours from the soundtrack in this video. Let's first consider what we mean by the Internet of Things, or IoT as it's known. We are all aware of the Internet, the global communication system that provides a whole range of services such as email, web and streaming video, to name just 3. But what is the Internet of Things? IoT is where devices are connected to the Internet, and for a device to be connected, it must be able to communicate. To communicate, it must have some form of intelligence and a reason to do so. A device will need to be aware of or control the world around it, and so it needs some form of input, sensor, and/or output, actuator. These then form the 4 basic elements of a thing, and the form of a thing is left to your imagination. Things are generally divided into 2 types. A thing can communicate with another thing, and this is given the term M2M, machine to machine, or it may be connected to a larger system that may process its data and turn it into information, which then may be used for human consumption, and we could see it on, say, an app. Intelligent refrigerators or toasters are often quoted as trivial examples of IoT, but burglar alarms that alert you by mobile phone are probably more useful. This is a beautiful example of the Oxford flood warning system, where remote battery-powered sensors report river levels from around the region and, amongst other things, display them in real time on this web page. Things may be anywhere and have been around for a long time. It's estimated that the crossing point where there were more things connected to the Internet than humans was way back in 2008. The projected explosion in the number of things is due to the rapidly increasing capability of things coupled to their equally rapidly falling size and price. We have yet to see whether these forecasts are achieved, but what is obvious is that the trend towards the thing-filled world has been well established already. Whilst sensors and actuators are important and worthy of a video of their own, we will now consider intelligence and communication more closely. We will also now refer to a thing as a device. Semiconductor technology has developed to produce smaller, cheaper and more capable microcontrollers and microprocessors. In fact, the increase in integration has led to devices called SoCs, systems on a chip, where numerous functions are all contained in a single device no larger than a small suite. When assembled onto a printed circuit board and combined with other devices, we know them as PICs, Arduinos, Raspberry Pis, some of which may also contain their small operating system, such as MicroPython. USB is the most common form of interface used to communicate with a device during the development process, and with this it's possible to upload and test programs. It's also possible to configure the inputs and outputs to a variety of sensors and actuators that may be analog or digital. Other methods of connecting local devices are via slightly more complex interfaces such as SPI and I2C, but these are the subject of another video. GPS is a useful facility, combining very high-frequency radio and a further processor. But all of this high-tech comes at a cost of increased power requirements, and this can turn out to be the Achilles heel of some things. As many devices are often remote, they also tend to be battery or solar powered. There is, therefore, a need to reduce power consumption. The power requirements of a thing may be reduced by running the processor at a low speed. A second method is to cause the whole unit to sleep. To be useful, the device has to awaken periodically to reconfirm its status, or be able to be awoken quickly and respond to any unexpected change in state. We will see how this state of hibernation affects how things are treated later. Another view of IoT can focus on the radio performance of a thing. Here we can plot the rate at which data may be sent against the distance it can travel. At one extreme is satellite communications, broadcasting extremely high data rates over very large distances. At the other, right down here, low bandwidth RFID chips and near-field communications devices that transmit very little data over millimeters. Networking is generally covered by the terms local area network, LAN, and wide area network, WAN, LAN, and WAN. The familiar Bluetooth transmits higher bandwidths over longer ranges, and Wi-Fi yet more still further. This region is occupied by mobile phone technologies, but this is achieved using fairly high power levels and certainly is not cheap. This region here represents long-distance, low-bandwidth applications, and this is where things tend to sit. They tend to be cheap, and by necessity or convenience, battery-powered. Power consumption is therefore a critical parameter when communicating. There are a number of different systems operating or still emerging in this area. The main two tend to be Sigfox and LoRaWAN. Sigfox is a closed and proprietary system, but LoRaWAN is an association of 500 companies dedicated to agreeing an international standard for low-power radio based on the LoRa modulation scheme. It's LoRa and LoRaWAN that we will focus on in this next section. LoRaWAN is the network that uses LoRa as an underlying radio technique, which is called modulation. Modulation is the word shortened when you refer to AM or FM radio. Here are the local powerful FM radio stations, nicely spaced out across the band at around 100 MHz. If we zoom in, we can see how the radio signal is modulated by the audio. Their quality relies mainly on their height above all of this background noise, which is everywhere. You can hear the effect of this as the power level falls. LoRa modulation is designed for a different purpose. It's a creature of the deep. It's designed for bandwidth sharing like Bluetooth and Wi-Fi and uses a technique that occupies a wider spread signal. It is at much lower power and can operate quite effectively where the background noise is actually higher than the signal itself. This quite remarkable technique was originally developed for military use, where the intent was to hide the signal. One technique is to use one frequency to transmit a 1 and a second frequency to transmit a 0. This is referred to as frequency shift keying, or FSK. You will see this referred to in the LoRa documentation. LoRa can use this technique for reference, but then goes further, spreading with a more complex signal called chirping. 1s and 0s are transmitted as interruptions in the normal cycle of a chirp sequence, as seen here. It becomes quite complex, but when used has the ability to hide, but can be seen clearly with a suitable receiver that becomes blind to the background noise. It's likened to conversing at a noisy party. LoRaWAN is built upon this ability, allowing devices to communicate over distances up to 15 kilometers in rural, quiet environments, or down to just 2 to 6 kilometers in noisy city environments. We say noisy here because all of the other users and all the electrical interference a modern urban environment produces. There are, of course, the other problems with radio waves, that they don't pass easily underground or deep inside buildings, particularly metal frame buildings. Tall buildings can act as radio reflectors, causing the signal to interfere with itself. Experience this for yourself by shouting across a large sports stadium. And of course, the signal gets weaker the further it travels. In the UK, we use the European band at 868 MHz. Others are available as seen here. They were referred to as ISM bands, industrial, scientific and medical. But the important point is that they are deregulated, license-free frequencies free to use. There are, however, still regulations regarding the maximum power a transmitter can emit and the amount of time spent transmitting. There are 3 frequencies that all devices use to join the system, that expands to 10 once they are accepted. All of this is handled automatically in the background, as we will see. Like Bluetooth and Wi-Fi, things need an access point to receive their radio signals and to join the network. In IoT, these are referred to as gateways, and one gateway can cope with thousands of things. A thing, or device, is usually referred to as a node when referenced in a network model, so a single gateway can deal with thousands of nodes. The gateways aggregate the communications from all of the nodes and pass them on to the internet, and we will investigate this in a moment. The construction and setup of a gateway is the subject of another video. Nodes close to the gateway receive a stronger signal, but this falls away as the distance between them increases. LoRaWAN has several techniques to deal with this problem. First, it has the ability, if enabled, to cause the node to transmit at a higher power. But this has the obvious cost of draining the node's power supply more rapidly. Secondly, it modifies the quality of the spread spectrum signal. This could be likened to speaking more slowly in human speech. You will see this in the references labelled SF7 to SF12, spreading factor 7 to spreading factor 12. The downside of this action is that there is less time available for the two to communicate, and smaller amounts of data can pass. The third solution to this problem would be to install another gateway, and LoRaWAN automatically deals with the process of accepting the new gateway into the fold. LoRaWAN is therefore a flexible, intelligent, low-bandwidth, bidirectional radio backbone designed to cope with millions of things, devices, nodes, in a shared high-noise environment. Finally, nodes can be classified into three types, referred to as Class A, B, and C. All devices begin as Class A, but may convert to B or C once they've joined the network. Class A allows the node to shout out a request to join the network regardless of the state of any other node that already may be communicating. It just interrupts rudely, possibly destroying any existing communications. In Class A, it can only receive for a very short period after its transmission. Historically, this behaviour is referred to as Aloha and is typical of early networking schemes that predate systems like Ethernet. Once connected, the device can negotiate to upgrade to Class B, known as beaconing mode, where additional time slots are allocated where it can receive data from the gateway. It's also possible to jump directly to Class C, known as continuous mode, where yet more time is allocated to the receive period. There is, of course, a cost to this activity, and this again returns to the power available at the node. Class C requires much more power. It's anticipated that the majority of things will remain as Class A. Our general model of a thing or node is therefore complete. In this next section, we'll select particular components to fulfill each role and prepare everything to construct a development platform for testing. In this example, we're going to use this Sodaq Mbili development board as the node. It may be purchased on its own or as part of a kit containing an array of sensors. On board is the intelligence, and this is connected here to the LoRaWAN radio module, which is intelligent in its own right. You may see nodes with all sorts of antennas, from cheap bits of old wire, formed coils, antennas printed on the circuit boards, minute resonators, through to stubby devices and some more elaborate arrays. As with anything, you get what you pay for, and the performance of the system depends upon the quality and the location of your antenna. Generally, it's a trade-off. The better the antenna, the lower level of power required, longer battery life. The board connects via the USB port, and to program it, you need to install the popular Arduino programming environment or Integrated Development Environment, IDE. The software for this is open source and free to download from this site. Select the option to suit your operating system, and do consider contributing something at this stage to the course. In fact, there is now a version that does not require downloading, allowing development to be carried out online, but I have no direct experience of that with this board. Follow the installation instructions once the download is completed and start the application. It appears like this. Full details as to how this IDE operates are provided elsewhere, but a brief introduction would be that the code, which is similar to C and called a sketch, is entered into this white screen area, the text editor, and may be checked by pressing this tick button in the toolbar, or checked and uploaded onto the Mbili board by pressing this arrow button. The results from both of these operations are reported down here in this black message area. There are two further steps that have to be taken before any code can run. Both steps can involve small potential gotchas. Once they've been completed, they don't need to be performed again. The first step is to install the profile for this particular Sodaq board. Click File, Preference, and add this UL entry into this field, and install. Next, click on Tools, Board, Board Manager. Enter Sodaq into this search field and apply to reveal these entries. Click into the area next to this Sodaq AVR board. Click the Install button to download. Once installed, click the Close button and return to the Tools board and select this newly installed Sodaq Mbili 1284P. Plug in the board and select Tools, Port, Serial Ports. It should appear here as a COM port. These options are based upon your local settings. If more than one option appears, then you may either disconnect the Sodaq board and see which COM port disappears, or work through the available options. Select Tools Serial Port to open the serial monitor and confirm the baud rate is set to 9600, and change this option to both New Line and Carriage Return. To confirm everything is operating, cut and paste the short program from the help file below into the white text editor. To compile and upload this sketch, click on the green arrow button here in the toolbar and watch the progress reported here and the uploading indicator here. You will have to be quick on a short sketch like this, but larger sketches will take more time. Watch for errors and warning comments in this message area. This warning regarding platform.txt is typical in the current versions of the software and may be safely ignored. Otherwise, this white text is confirmation of a successful upload. Now click Tools, Serial Monitor to open a separate serial monitor screen to see the output from the sketch, confirming that everything is working, and we can progress to the next section. The last step confirmed that the Arduino IDE understands the hardware of the Sodaq board and is capable of communicating with it effectively. In this step, we're going to download some support software that we can use as programming code and some support code that will be stored in what is known as a library. All of the code has been compressed into a zip file that has to be downloaded and decompressed before we can use it. In a browser, click on this link, which should cause a zip file to download. Once downloaded, unzip the file and keep a note of the location of the contents. These now need to be referenced in the IDE. Click Sketch, Include, Library, Add Zip File, and navigate to the location of the extracted zip folder. Enter the folder that will typically include these three folders. Click on the first and press Open. The results should be confirmed in the message window. Go back and repeat the process for the other two folders. Don't click on either the zip folder or the main extracted folder, as the IDE will not recognize them. This completes all of the downloading of the software, and the fun can begin. None of these processes ever need to be repeated for this setup, but it's typical of what is involved should you purchase a different board. Inside the downloads are some example sketches by way of demonstration. To load the first, click File, Examples, AOT, LoRa, IoT, and Demo. The sketch opens in another window and may be inspected by scrolling down the screen. Rather than working on the original code, it's wise to make your own copy, so use File Save and rename if necessary. This program is made of two connected sketches that are linked to work together. They may be seen by switching between these two tabs. One is the main sketch, and the other is a skeleton file called keys.h. The keys file has been separated out because once it's been configured, it may be used as a reference by other programs, rather than individually changing each one. It contains, or will contain, the individual addressing and key details used to get your node onto the internet, and recognised as the secure source it is. The next step is to obtain and insert these details to complete these empty fields. To do this, you will need an account in the cloud to connect your thing. Please note, once again, that this is a UK government-funded project only available to qualified individuals and organisations here in the UK, and then only those within the range of a digital Catapult gateway. Globally, you can freely obtain the details you require and a similar but open source service by registering with ThingsNetwork.org in Amsterdam. So sign up here. Once you've registered an account, you will be able to log in and have access to what is referred as a dashboard. This dashboard is where you register your devices and connect them to the wealth of cloud-based functions. Phase 1 is to register the device. There are two methods of connecting devices, and these are entitled Activation by Personalization, ABP, and Over-the-Air Activation, OTAA. Over-the-air activation is more secure and likely to be the option adopted for final products, but here we will use ABP for simplicity and speed. Once connected, there's no difference in the operation of either type of connection. Enter a device name of your choice and ignore the Edit button. Click Next to see the available linking options. Click the All Things Talk and enter the reference nickname of your choice. The helpline at the top of the screen explains, in order to successfully connect your device, please copy and paste the following information into All Things Network Maker, which will guide you through the setup process. The link here converts between two formats of code. One is called the string format, and the other, the far more friendly UINIT 8. It's the string format that is required for the direct and convenient cutting and pasting into the keys file. Do this. Care has to be taken to ensure that not just the numerical format is followed, but the punctuation as well. Press File, Save inside the Arduino IDE to save a local copy of these details. These are the individual settings for your device alone. This completes the device registration process. The usual move would be to click on this green Continue to All Things TalkMaker button, but this is running ahead. This step is the subject of the next part. The aim of this part is to prove that everything is working up to this point, which is a significant achievement. Hold the dashboard open for the moment and bookmark it for convenience. We will return to it in a moment. Now, go back to your device. Select the serial monitor. If it's not visible, click on your copy of the demo program and select Tools Serial Monitor, and select 56,000 from the pull-down, and when selected, just close the window. If you've lost your way at this point, you can click on the small Arduino program selection icon and either select your copy of the demo process or just close all Arduino windows and restart. Typically, it will reopen with your copy of demo program last used. Connect the button board to the socket shown. This may be done without removing the power. As a note, Arduino devices do store their last program even after the power has been removed. We are ready to proceed by pressing the arrow key and checking the upload progress bar. Again, this orange warning may appear, but this is a short-term issue that can be ignored. Any red text here needs to be investigated, but white text indicates that the program has been compiled correctly and uploaded onto the Mbili. Now, reopen the serial monitor by selecting Tools Serial Monitor. Hitting Ctrl, Shift and M is the keyboard shortcut for this option. Opening the serial monitor sends a restart message to the Mbili. This should be seen within a few seconds. If the output is gobbledygook, then check the baud rate here is set to 56,000. If all is well, the title line appears, followed by the ready to send line. Any button press is acknowledged by this message. Pressing the button too rapidly introduces the first experience of how IoT is designed for low bandwidth traffic. Back comes the response. Maybe the last couple of packages were sent too quickly after each other. Minimum of 15 seconds recommended. There is a limit to how much data may be transmitted, and we have hit it here. Confirmation that the remote end is receiving data can be seen by returning to the dashboard and clicking on the Devices link, and then here on this cog icon and Gateway Packets. This screen displays all of the packets received by the system. This is a sign of success. A counter indexes the packets, and the small coloured arrows display whether it's an uplink to the internet or a return downlink packet. Packets that are confirmed have ticks in the type column. This column displays the date and time, and here is the address of the gateway responsible for transferring the communications. Note here that there are two different gateway addresses. There are two gateways within the range of my device, and both receive packets and forward them. Gateways are naive. They simply pass on all packets they receive. It's not the role of the gateway to become involved in dealing with duplicate packages. This is the function of the network controllers. Finally, this is the data payload of the package. Clicking on this eye icon reveals more data about each packet. It's the metadata identifying the lower level details of the packet. Included are the addresses and IDs of the network components, along with the date, time and GPS location. RSSI is the receive strength signal indication, how strong the signal was, and the modulation details, including the frequency used. All of these details are combined to develop a more detailed view of the operating environment and used to enhance the overall network performance. All of this, of course, is only possible if the device is in range of a suitable gateway. During the filming of this video, a new world distance record was achieved by the guy with the Swiss accent. And, spoiler alert, it could have been over 100 kilometres. This completes the first part of this video series. In part 2, we will look at how these radio packets are processed and displayed. Where did he get that dynamite from?